Hello everyone, my name is Wen Zhiyuan. The topic of my speech today is how to compress encrypted data. My speech will be divided into four parts. They are inspiration and contribution, preliminaries, compression via sparse polynomials, compression via IBLTs. Okay, now let me introduce the first part, inspiration and contribution. We all know that in the early days, encrypted data was incompressive because the encryption algorithm itself was designed to make the data difficult to understand and interpret, and the encrypted data became random and unpredictable. Therefore, the size of the data cannot be reduced by conventional compression algorithms. Compression algorithms usually reduce the size of data by finding repetitive patterns and regularities in the data. But the purpose of encryption algorithm is to disrupt the patterns and regularities of data. So compressing encrypted data is almost impossible. However, in this paper, the authors propose two encryption algorithms that make it feasible to compress encrypted data. The author mentions a searchable encryption key and assume a client, Charlie, who holds a vector of data element M1 to Mn and wish to store it remotely on a server Sally. Charlie used the key to encrypt the data before sending it to Sally. In the future, when Charlie wants to search a vector and retrieve all elements that match a secret keyword, Charlie will first send a short keyword-related hint to the server, which the server uses to cipher the vector C1 to Cn into a new vector. If the searched information matches Charlie's keywords, then it will return 1, otherwise it will be 0. After completion, the server obviously compresses the new vector C under the assumption that no more than t ciphertexts were matching the keywords and send it back to Charlie. If the assumption about the sparsity of the new vector C was correct, then Charlie successfully decodes the vector and obtains the desired result. If the assumption was not correct, then Charlie may not be able to retrieve the output. During this process, encrypted data was inadvertently compressed. Choi has made great contributions to the optimal compression algorithm. He compresses C into a bit string of length omega t c k plus log n, where C is the length of one ciphertext entry, K is the correctness error defined as the searchable encryption example. Choi showed that Charlie can correctly decode the vector with probability 1 minus 2 to the power of minus k. Both compressing and decoding are computationally correctly and efficient. However, this algorithm also has a problem. That is, the solution is expensive. It needs performs omega tn plus kt log t, homomorphic additions, and omega tn, homomorphic multiplications by the constants. Liu and Tromer introduced oblivious message retrieval. Consider a server, Sally, with a public bulletin board and three clients, Charlie, Chunky, and Chris. Each client can publish encrypted messages on the bulletin board for any other client, and the recipient of the message is hidden. When Chunky wants to retrieve all messages addressed to him, he generates a short identity-related prompt and sends it to Sally. Sally can use this hint to inadvertently generate a short message with all the encrypted message related to Chunky. Although this method compresses the encrypted data, it is very expensive from an efficiency point of view. During the decoding process, Chunky needs to perform a Gaussian elimination on a matrix of size OT multiply OT, which will generate a computational overhead of omega the third of power of t. And the ether does not provide a good optimization method. The author of this paper proposed two new algorithms for compressing sparse encrypted vectors. The first one uses polynomial compression, which has a very high compression rate, and the compression vector is only 0 sigma t bits large. During the compression process, O n log n homomorphic additions and equally many homomorphic multiplications by constants needs to be performed. However, the decompression of complexity of this scheme is OT root n, and the decompression time is longer. The second is a solution based on random hashing. During the compression, O n k divided by log t homomorphic additions and constant multiplication need to be performed, where k is greater or equal to log t. During decompression, the complexity is OKT divided by log t. The second part, preliminaries. First is homomorphic encryption. Homomorphic encryption is a very important encryption method in this paper, which allows computational operations to be performed in encrypted states without decrypting the data. In other words, homomorphic encryption allows data to perform operations such as addition, multiplication, and logical optimization in an encrypted state. The result is still in an encrypted state, and the planned results can only be obtained after decryption. A homomorphic encryption scheme C is defined by a tuple of PPT algorithm, generation, encryption, evaluation, and deterministic that work as follow. The key generation algorithm takes the security parameter 1 to the power of lambda as input and returns a secret key sk and public key pk. The public key implicitly defines a message space M and ciphertext space C. We denote the set of all public keys as P. The encryption algorithm takes the public key pk and message M belong to big M as input and returns a ciphertext C belong to big C. The evaluation algorithm takes the public key pk, a function f, m to the power of n to m to the power of m, and a vector c belong to uh, big C to the power of n of ciphertexts as input and returns a new vector of ciphertext c belong to c to the power of m. The, the deterministic decryption algorithm takes the secret key sk and ciphertext c belong to big C as input and returns a message m. Polynomial kung fu is an algorithmic technique in computer science for efficient operations in polynomial rings. It is mainly used to solve polynomial evaluation, polynomial interpolation, polynomial multiplication, polynomial division, and other problems. The core idea of polynomial kung fu is to express polynomials as point values, that is, to evaluate polynomials at some specific points to obtain a set of point values, and then perform polynomial operations through the relationship between point values. This method can greatly reduce the time complexity of polynomial operations, thereby improving the efficiency of the algorithm. Fast Fourier transform is also a very important method in this paper. It is an efficient algorithm for calculating discrete Fourier transform. Its time complexity is O(n) log n, which is much faster than the time complexity O(n to the power of 2 of the general DFT algorithm. The core idea of the fast Fourier transform algorithm is to decompose the calculation of discrete Fourier transform into multiple smaller discrete Fourier transform calculations, and then curiously merge these small discrete Fourier transform calculations into one large discrete Fourier transform calculations. This divide and conquer idea can greatly reduce the amount of calculation, thereby improving the efficiency of the algorithm. Invertible Bloom lookup table is a data structure based on Bloom filter, which is used to solve the problems of data synchronization and data differences calculation. IBLT can be used to quickly calculate the difference between two datasets or to merge two datasets into one. For Bloom filter, it is commonly used data structure used to determine whether an element exists in a collection. Bloom filter maps elements into a bit array through multiple hash functions and set the corresponding bit to 1. When it is necessary to determine whether an element exists in the set, the element is mapped to the bit array through the same hash function, and it is checked whether the corresponding bits are all 1. If any bit is 0, you can be sure that the element does not exist in the set. If all bits are 1, the element probably exists in the set. IBLT is developed on the basis of Bloom filter. IBLT maps each element into multiple buckets and sums the values in each bucket. When the differences between two data sets needs to be calculated, the two IBLTs are merged and the value in the same buckets are subtracted. If the value in a bucket is 0, it means that the elements in the bucket exist in both datasets. If the value in a bucket is positive, it means that the elements in the buckets only exist in the first dataset. If the value in a bucket is negative, it means that the elements in the bucket only exist in the second dataset. The compression algorithm takes the public encryption key PK as well as a vector of ciphertexts C from some family FPK of ciphertext vectors as input and returns some compressed representation theory. The decompression algorithm gets the compressed representation as well as the secret decryption key as input and should return the decryption of C. And below is the function of ciphertext compression scheme. The third part I want to introduce is compression via sparse polynomials. The first construction proposed by the author is compression via sparse polynomials. This construction treats the spare encrypted vectors C1 to Cn as coefficient representations of spare polynomials. The author used fast Fourier transform to homomorphically evaluate this polynomial. This encrypted evaluation will constitute the compression of the vector. To obtain the origin vector during decompression, we simply decrypt the evaluation points and interpolate the corresponding space polynomial. Below are the definitions of fast Fourier function and valid low-Hamming weight ciphertext vectors. The author proposes such a theorem based on the above method. Let E equals to Gn Enc Eval Dec be an additively homomorphic encryption scheme with message space M equals to FQ with ciphertext size C equals to C lambda. Let N T belongs to begin be integers such that N is less than Q and let W belongs to FQ be a 2 multiplied by T plus 1 th primitive root of unity. Then compress decompress is a 2 multiplied by T plus 1 divided by N, compressing perfectly correct ciphertext compression scheme for family FT. To prove that, we can let C is a validity condition. DEC SKC is a vector of Hamming weight that most T. A T space polynomial of degree at most N. We can then correctly interpolate this sparse polynomial from the 2 multiplied by T plus 1 evaluations resulting from DEC SKC W to the power of 0 to the W to the power of 2T plus 1. Then we can get interpolate FFT DEC SKC W to the power of 0 to W to the power of 2T plus 1 equals to sparse DEC SKC. From this formula, we can find that this scheme is 2 multiplied by t plus 1 divided by n compressing. The fourth part, compression via IBLTs. The second construction proposed by the answer is compression via IBLT, which is based on a variant of the reversible Bloom lookup table. This construction, given a ciphertext vector C, inserts the corresponding non-zero plaintext homomorphically into the encrypted IBLT. The encrypted IBLT will then constitute the compression of the vector. However, this approach faces two problems. First, IBLT's insert operation requires hashing the value to select the cell to insert into. It is difficult to do this because we do not have access to the plaintext. The solution to this problem is store pairs D and D. The position of the inserted value can be diverted only by hashing D, because the in-text D is public and unique. Second, we don't know which ciphertexts correspond to non-zero values, so it is not clear how to insert only those ciphertexts. The solution to this problem is choose a random value vector k initialized to matrix M and K. After declaration, for any cell ij that only contains a single value MD, have Mij equals to MD and Kij equals to MD multiplied by KD. Pseudo-random vectors are also an important concept, allowing us to sample short descriptions of long vectors. Based on this, the author proposes an efficient algorithm which can recover the position of a given entry in the vector in time independent of the vector length. The description length of the vector is O lambda, and in O polylog n fetching of a single entry and indexed, a recovery is possible. The author proposes the following theorems. For all indicates I belongs to n, it holds that indexed S entry Si equals to I. For all k which does not belong to entry Si or Si I belongs to n, it holds that indexed Sk equals to bottom. And let PRP be a secure family of pseudorandom permutation over some f. Sample entry index is a secure wunderbar secure random vector with indexed recovery for universe k equals to being to fade b. B is belong to f. And below is how to prove it. The authors demonstrates here a useful lemma that allows limiting the probability of false positives when trying to detect cells with only one entry in the IBLT. If for some set of at least two non-zero messages, corresponding to indicates I contained in N. It happens to hold a disk function kj. So it can limit the probability of its happening by selecting k entries from a sufficiently large space. And here is the proof of this helpful lemma. Construction of ciphertext compression from IBLTs. Populating the IBLT involves the homomorphic evaluating an inner product between the encrypted vector and a plain vector. So, the answer uses inner product functions. The following is the definition of inner product functions. The class of inner product functions is the set of functions zip with fa. The family of ciphertext vectors, the construction is applicable to is then exactly those ciphertext vectors with low Hamming weight and allow the evaluation of inner product functions. And for any div-valid vector of ciphertext, it holds that PR decompressed secret key compressed public key C equals to spares DEC secret key C equal PR decompress 1 compress DEC secret key C equals to spares DEC secret key C. Also, we have if sample entry index is a secure procedural random vector, it holds for any key pair sk pk and any vector c that like this picture below. This is another claim made by the author. If the Hamming weight at most t for any vector of ciphertext, we have PR decompressed compressed DEC secret key C equals to spares DEC SKC is less or equal to O 2 to the power of minus K. And how to prove it is compress 6 outputs and IBLT for pairs containing all elements of S is not equal to 0. And decompress 6 is the same as list. Update 6 is the same as PO. And so we can get the following function, and so it can be proved. And for the future work, these are some directions that I think the author and other professors can research in the future. First, I thought it would be possible to find some algorithms that would reduce both compression and decompression complexity and have smaller compression vectors. In this paper, no matter whether it is polynomial-based algorithm or algorithm based on hash algorithm, these points cannot be realized at the same time, and only part of them can be realized. Second, I thought it might be possible to think about how to compress encrypted data from a completely new perspective without compressing sparse encrypted vectors. Thank you for your listening. And here is the detail of the paper.